Okay, we're going to do 5-2. A little early, too. It's called Riemann sums and definite integrals. And our goal here is to find the area under a curve. We've been finding area under the curve with like 4 rectangles and getting a good estimate. But what I'd like to do is find a better one. I'd actually like to get the exact area. So we're going to start with 2 rectangles, and we're going to go to a whole bunch of rectangles, and then you can see what we end up getting. What's going to happen on the exam is you're not going to have to do these Riemann sums by hand. You'll either be doing them with a calculator or geometry, or something that's going to happen in the future will show you how to do that. But you'll have to be able to recognize that this is what it is, and that's going to be the hard part. And I'll try to bring in those examples from the AP multiple choice. It's been on every multiple choice exam I've seen, so I do expect it to be on them. So I graphed y equals x squared. Ignore the scaling on the bottom. And we are going to break this into 2 rectangles. So we're going to learn some terminology today, too. There's a lot of terminology. And this is called a Riemann sum when you find the area under the curve using rectangles. It's just the name of the guy. That's it. We're going to also work on the calculator, and we'll talk about what does it mean to be able to integrate. Okay, so let's put a couple rectangles in there. I'm going to do it as best I can. Oh, I don't know if you can see that. Can you see that? Oh, I picked the wrong one. I can't. I wish I could. I just can't. That's better. Because they're broken. Well, we would if we could, but they're broken. Okay, did I get that right? More or less. And we're going to use the right endpoints of our rectangles. There. Not too bad. Yeah, that's the problem. Okay. They're supposed to be the same size, as good as I get. They're going to be the same size. Okay, we want the bases to be equal, just because it makes our arithmetic easier. But Riemann says it doesn't really matter if they're equal. But for our purposes, we want them equal. And I'll show you what we're going to end up getting with this. Okay. So we're going to do the base of this rectangle, which is pretty easy. It's what? 1, right? And how do you find the height of the rectangle? It's the value of the function at 1. I'm not going to use the value of the function at 0. So when you do these rectangles, you're either going to use the left endpoint or the right endpoint, but you're not going to use both. On the trapezoidal rule, you will. Plus, and then I have another base of 1, and the value of the height of this function is f of 2. Well, let's see, what was f of x? F of x was equal to x squared. Is this going to be an overestimate or an underestimate? Look at the picture. It's over. It's going to be too big. So it's going to be 1 times 1 squared plus 1 times 2 squared. So that's going to give me 1 plus 4. The area is 5. Really way too big. Is that okay? That's a little better. Any problems with that? We've been doing this. If you did the homework, you've been doing it. Okay, let's try 4 rectangles. Are we going to get better with 4? Yes or no? What do you think? Yeah. Now I'm going to do my best I can to get 4 in here equally spaced. I'm not going to, I'm going to actually make these more complicated a little bit. It's not too bad. I'm getting better at this. Okay, so now if this is 2 and I have 4 rectangles, what size will the bases be? A half. So that's a half, and this is going to be 3 halves. I want to do things in fractions. Because I took 2 minus 0, and I divided by 4. Then we do 4 rectangles. If this is $2 divide by 4 people, it'll be 50 cents each. No, what's the base of my rectangle going to be now? What's the base of the rectangle going to be? Not 2. 1/2. It's just this length right here. So it's going to be 1/2 times, and it's the value of the function at 1/2. That's the first point. Plus, in the base, I want to choose the bases all to be the same at 1/2. Then it's going to be f of 1. But I'm going to make that 2 over 2. Because I'm looking for patterns. Plus 1/2. And it's f of 3 halves. Plus 1/2. And this is f of 2 halves. No, 4 halves, sorry. 4 halves. And then we're just going to substitute it in to our formula, which is f of x is x squared. That's it. It's not particularly hard. It's tedious. I'll grant you that. So there's a 1/2 for each one of these. So I'm going to factor out the 1/2, and then it's going to be f 1/2. But that's 1/2 that I'm going to square, because it was x squared, plus 2 halves squared. At least I think you can see patterns better when I write it like this. And some of you on your homework recognize patterns and use that to your advantage when you did your homework. Then this is 3 halves squared plus 4 halves squared. And that is just arithmetic, right? It's better than the 2 rectangles. It's still not great. So this is 1/4 plus 4 halves, 4/4, sorry, plus 9/4 plus 16/4. And then you just add them up. You know, 1 and 4 is 5, and 9 is 14, and 14 and 16 is 30. So it's 1/2 times 34, or 38ths. And how big is that? That's approximately, well, not approximately, that is, 8 goes into 30 3 times with 6 pieces left over, so it's 3/4. So it's still too big. And we can actually find out exactly what it is using our calculator if we wanted to. But let's go and do the next problem, and then we'll use our calculator. What happens if I add more and more rectangles? My answers will get what? Better and better. I hope they get better. Okay, that's what we're going to do. This is the part. This is so far easy, yes. Look at your picture. The rectangles are outside. Now, how do you know? I would draw the picture. It has to do with increasing, decreasing, not concavity. You might think it has to do with concavity, but it doesn't. It's increasing, decreasing. So if I have a decreasing function, and I put my rectangles underneath it, or not underneath it, hitting on the right side, you see this is underneath. See how those are underneath? That'll be an under estimate. It's the increasing, decreasing piece. So that's a problem. I just draw the picture and say, oh, okay, see, it's going to be over. Okay, you ready for the infinite case? That's what we're going to do. Now, what they're going to ask, we're going to get this in sigma notation, and we may write it out by hand and in sigma notation. That's what you're going to see on the exam. And then you're going to look at it, you're going to recognize, and you're going to say, oh, that's a Riemann sum 4, and you'll find other ways to do it. It's always been on the exam. So I'm just going to put in a bunch of rectangles here. I'm going to make mine equal width as much as I can. Whoops. Etc. And this is 2. And now I'm going to figure out what each one of the bases are. I'm choosing to make all the bases the same size, but in reality, I don't have to do that. But I'm going to make them all the same size. So how big is that base? I'm going to divide this into n rectangles. We'll just call it delta x if you'd like, for now. So that's delta x. And then I'm going to name my x-coordinates, because you know what? I don't know where they are. This is the first one. Then this is the second one. This is the third. And then there's a whole bunch in between. Infinite number of rectangles in between x3 and 2. So I'm going to talk about a rectangle out here, and I want it to represent anything between 0 and 2. And I'm going to call that x sub I. And then this is x sub n. So let's find the area. It's not that bad. It will get to look bad. The problem is it's not going to look like a function when we're done with it. It's going to look weird. So how do I find the area of this? What's true about all the bases? They're all the same. So let's just factor that out right now because it's easier. And then I find the value of the function at each x-coordinate. So it's f of x sub 1 plus, then it's the y value at x2, and we'll figure out what those are, plus the y value at x3, plus, then there's the one in between there, and maybe it's the 90th, maybe it's the millionth, I don't know, but we're going to find the value at that particular random interval, so we'll call that x sub I. You'll see why I want to do that. And we'll end at f of x sub n. Now, can we write that with a sigma? Remember how to do sigma? Did a little bit of it, but some of you forgot to turn it in with your homework. It's delta x. Forgot my sigma. And remember how we can start with I as just a counter? So I is going to start with what number? 1, and it's going to go up to n. And delta x is just going to be a constant, so we chose it that way. And then this is f of x sub what? I. I don't know if there was one in the homework. In the old book there was. But that's all this is. So I don't want to write all that out. It takes me forever. So somebody invented sigma notation, and that's what that means. This line right here means this line right there. And if I had my summation looking like this, I could still figure out what it is. Well, I'm going to just... No, let's go ahead and do this in the same order. Okay, we got to figure out what delta x is and what x sub I is and see what it's going to look like. This is what you would have to do. This is what Leibniz and Newton and Riemann, all those guys did. They said, okay, I want a better guess than 4 rectangles. I want an infinite number of rectangles. So I got to figure out what delta x is now. Now, how big is this width? If the whole width is 2 and you divide it into n rectangles, how long is this segment? What did you say? 2 over n, that's right. Remember, we had 2, we divided by 4 rectangles, we got a half. This is equal to 2 minus 0 divided by n, or just 2 over n. Okay, that's my delta x. Now for the hard part. What I consider hard part. No place to put this. I guess I'll do it right here. Now, what's x sub 1? We're going to look for patterns. X sub 1 is the coordinate. Remember the first one we did, when we made delta x a half, we went to a half. This is going to be the first coordinate we'll evaluate our function at. This width is delta x. So you see x1 is one of those little delta x's. You see that? So you're just going to go over one of these intervals. And so that's equal to 1 times 2 over n. Some people want to multiply that out. You can, you just won't see the patterns as easily. Okay, what about x2? How many delta x's do I have to go over? 2. As long as I make them the same size, I can do this. This is 2 delta x, which is 2 times 2 over n. Okay, let's do another one. Let's do x3. x3 is how many delta x's? 3, because you're going to go over 1, 2, 3. That's 3 of those guys. So that's 3 delta x, which is 3 times 2 over n. I'll squish it in. So what's x sub I? Whack a space here. What's x sub I? You're going to go over I intervals. It could be the hundredth, millionth, whatever. It's I times delta x. It just depends on how they write it on the exam is the problem. So this is I times 2 over n. That's a lot of work, but it's just geometry. And now it's going to be a little more abstract looking, because now it doesn't look like f of x. So let's go ahead and put these guys in here. Which form would you like? I can do both. I can do this, or I can go right to sigma. Your choice. Oh, you like sigma? Okay. So it's sigma I equals 1 to n, and delta x was 2 over n. So there's my base. And my height was f of x sub I. So it's f of, and my x sub I was, it's going to look weird, but it's 2i over n. Just a little more. And in the old book, we spent days. We did this with several functions, worked these out by hand. I'm just showing it to you and then showing you what you have to do on the exam. So it's the summation I equals 1 to n, and it's 2 over n. And remember, f of x was equal to x squared, right? So I'm just going to square that. So it's 2i over n squared. That does not look like an f of x. Doesn't look like there's any x's in it. Remember, this is the base, the width of the base, that's delta x, and then this is f of x. What you have to do is see this and see that that's just f of x, it's x squared, and that that's just the change. Not easy to do, by the way. Well, let's just do a little more. We have to recognize what it is, but just to show you what we did in previous classes, we pulled this one out front because we can. It's property sigma. So it's 2 over n, which really makes it nice that we're not doing them by hand anymore. And then this would be squared, so it's going to be 4i squared over n squared. And I can pull out anything not related to I. I can pull that again through that sigma. So I can take 4 over n squared right out of there. And when I take this, 4 over n squared, I'm going to multiply it by the fraction I have in front, and I'm going to be left with 8 over n cubed. And then it's the summation I equals 1 to n of I squared. And some mathematicians had no light a long time ago, and they figured out what that would be. This thing ends up being, I think I'm right, n plus 1, 2n plus 1, oh, I'm missing an n, over 6. And you would substitute that up in here in place of the sigma, and you would do all the algebra and simplify it, and you will end up getting 8/3 is what you should get. A lot of work. That's not what they're going to have you do. They won't even give you anything that looks like this line right here. Oh, I can't do it. But when you see them, and I'll get copies to you, you're going to have a hard time with it. So you got to understand this concept right here of this delta x being 2 over n. How do I get delta x? To get delta x, I just take the difference between a and b. So it's b minus a over n. And what we're going to do is we're going to come up with a different notation. So Riemann says, I don't want to write this. I don't even want to do it this way. There's got to be a better way. So all these words are what we're going to get to. Instead of when you do these areas, by the way, this is said to be partitioning this area. So here's my curve. You can't see it very well, but here it is. You're dividing the curve into regions, rectangles. But what I want to do is get the biggest rectangle. This looks like the one with the biggest width. I want that width to go to 0. Now, this is the biggest width. What's going to be true about all these other widths? They're smaller. So if this goes to 0, then all the other ones have to go to 0. In effect, I end up with this being a solid, it'll be shaded solid. You won't see these little lines here like this. I want this base to become infinitely thin. So then my little rectangle will look like a line. And then I'm going to put another one next to it. Did you see how it's going to become solid? In other words, you're putting more rectangles in. I can't say I'm going to put in an infinite number of rectangles because this one could stay there where it is and I could still put an infinite number of rectangles under this curve. That's a problem. Then this answer here, when I add up the rectangles, will not be exactly equal to that area. So I want the biggest one to go to 0. But what you guys are going to think about, you're going to think about them all being the same width, and I want delta x to go to 0. It's the same as saying the limit of my rectangles is n goes to infinity. I'm going to put an infinite number of rectangles in there. And they're so skinny that they fill up this whole region. So if I get my calculator out, and just let's look at that again. Y equals, I'm going to clear that out. Let's just do x squared. Whoops, I don't want that. X squared. And now we look at my window is. Oh, that's okay. And let's graph it. Okay, there's y equals x squared, right? I want to put an infinite number of rectangles in there. All skinny. It's going to fill it out as a solid region. Actually, what's happening with your calculator is it's exactly what it's doing. It doesn't know how to do calculus. So it goes second, calculate, it draws maybe 100 rectangles. I don't know. But number 7 says find the area under the curve. So I'm going to do 7, and we're going to start at 0, and we're going to go to 2. See those rectangles? They're going really fast, but that's what they're doing, adding more rectangles. That's why you want to use my Riemann sum program. If I gave you the program, and I don't have it on here, I'm sorry. There. I want to second calculate. So my window, I just left it from 0 to 2, and then I knew that the y's got up to 4. So I'm going to clear my drawing. Let's do it again. Because I won't do it again. And so if I go to graph, there it is. And I want to put rectangles in. The Riemann sum program, if you put 100 rectangles, it will look like this. It'll show you all those rectangles, but you won't see them because they're so tiny. So now I'm going to do second calculate, and I want to do 7. We're going to talk about that notation. I'm going to start at 0, and I'm going to go to 2. And there it is. Is a finite number of rectangles. Your calculator can't do infinite number, right? So that's all Riemann did, is he said, well, let's divide this up. I know this is hard. Let's take the biggest one and say, remember, this is the biggest rectangle, the widest rectangle. We're going to make it infinitely thin. If it's the widest one, all the other ones have to become infinitely thin as well. And I don't even care where I evaluate my function. I could do someplace in the middle. I could do someplace at the end. It doesn't matter. I don't have to be consistent. But in terms of using those special formulas, I do have to be consistent. So it's not a big deal. And then not only that, this y-coordinate is positive. But what about this y-coordinate? Let's talk about the y value here. It's negative. So since the base is positive and the y is negative, the integral is going to be negative. This is called a signed area. Oh, you'll get this. It's not that bad. No, if it just drops below the x-axis, then that area is negative. If you go backwards, you have to worry about that too. Yes, this is the signed area. Now, if I were to paint all of this, my answer would be not negative for sure. But an integral, because you're actually using the y value here, which is a negative number, will actually be a signed area. And we're going to ignore a lot of this reading. So I just want to keep it simple. And then just talk about signed areas. Now, this is the part that's really ugly. All we're going to do is put in a whole bunch of rectangles. I want to fill this all in. So I want my rectangles to be really thin, and I want to add them all up. And that's what this says. You'll see it. It will work for you. What? This is what this is saying. This is the area under the curve. It's the signed area. And Riemann gets credit for it. But the thing is everybody freaks out because it looks so ugly. I said, just think of it, it's a Golumbesky sum. It's this guy's name. Signed area under the curve. And I'm going to clean that up so it looks better. Because you'll feel more comfortable. Now Riemann says we're going to divide them up. All the rectangles can have different bases. They're called partitions. Don't worry about it. We will keep ours so that our bases are all the same size, and so our number of rectangles will go to infinity. In effect, it's the same thing. And we're going to add these all up. I'm going to keep delta x the same size. I is equal to 1 to n, and it's going to be f of x of I, and it's delta x. It's called a Riemann sum. You're never going to have to do that with the n's like I just did. But remember when I just did all that and I showed you what x of n was and all that stuff? You're going to have to recognize it. That's all. So he says, sigma's nice, but you know what? It's still more than I want to write. So I'm going to make up my own notation, which he did, and it's called an integral symbol. That's what that is. So this means integral. And that just means sum. That's all. And then he says, well, I want to find the area between 2 points. Let's call it A and B. And then here is the height of my rectangle. That's just f of x. And there's the base of my rectangle. Well, I want the delta x's to be really little, so we'll call them dx's. So these are the same things. These are equal. That one with this one. So when you see this limit and this ugly looking stuff with sigma, you go, oh, it's just an integral, and you write it this way. And then how do you find the area under the curve? Geometry, if it's all possible. You may have to use your calculator, or there are some other techniques, which we'll get to. But right now, as far as we're concerned, we're just going to look at geometry. And that's the signed area. So all you have to really know is that this ugly looking limit, Riemann's made a definition, and he says, let's call it this, and it's called a definite integral. There'll be indefinite ones as well. I don't know why it's integral, but it is. So, let's do some problems. Right here, it talks about the existence of definite integrals. It's kind of interesting, as you can always find one, provided there's a limited number of discontinuities. But you could have a function that's not continuous. Remember, to do derivatives, the function always had to be continuous. What about the greatest integer function? Remember that one? Can you find the area under the curve? What's the area under that one little piece? 0. What's the area under this little piece? 1. There are big breaks in the graph. I can't find derivatives there. What's the area under this one? That's 1, that's 1. So what's the total area here? 3. You guys play those dot games. It's the same thing. Kind of cool, though, because derivatives, you always have to be continuous, but not integrals. And that's just saying what I already said, so I'm not going to go through this again. I don't know why I have all that stuff there. Okay, so let's do a problem, because it's a lot easier than you think. Getting to understanding what's happening is the hard part. So that's a Riemann sum. I want to write it as an integral. So here is my height. Unfortunately, they're not this easy on the exam. And that's the base. So they want you to write it as an integral. Okay, A and B are the interval over which you want to find the area. So what's the lowest bound? -1, 2, because it says negative. -1, 2, 3. And what's the function? What's n sub k? It's really x, isn't it? I know it doesn't look like x, but that's what it is. So it's 3x squared minus 2x plus 5. And then you need the base, which is the dx. And there it is. And you can use your calculator. If you want me to get the calculator out and do that? Okay, we can do it with the window like we just did, or we can do this FNINT. Now, bear with me. If you have the old operating system, and what you will enter will look like this. FNINT. I get all confused with the parentheses, so I put my function into y1, and then I don't have a problem. Because sometimes, especially as a rational function, you get all these parentheses, you lose track where you are. So it's y1, and then it's looking for this differential, saying I want x's, and these are always going to be x's, and then you're going to go from -1 to 3, or from A to B. Now it's going to look different on the new operating system. So, where is it? And now also on the exam, this integral that I have right here is what I want to see, not the FNINT. You can write it down, but they won't even look at it. It has to be in calculus notation, not calculator notation. So y equals, I'm going to clear that out. I'm going to put in 3x squared minus 2x. And what's the other? Plus 5. Plus 5. I'm not gonna graph it because I don't know where it is. Then I have to worry about how tall it is. I'm just gonna use this function on math. Now, old operating system, you're gonna press math and you're gonna go down to 9. The new one, I'll show you, is still here. It's still the same on the new one, but it's also, if I go alpha and window, it's also right there. And now mine is going to look like that. I can't get mine to look like the old one any longer. Sorry. And so this is -1, and that's 3. Those of you with the old system, you're going to have to type in y1, comma, x, comma, -1, comma, 3. I like this. It's definitely an advantage, I think, because you're writing it in the right way that the graders want to see it. And then this is y1. Now y1, you can get under bars, or if we're in the new operating system, I go alpha, in the calc, and there's y1. A is your lower limit, and then your upper limit. And I'm sorry, I can't go back to it. I thought if it went to classic, it would go back to it, but it doesn't. It still stays with the pretty print. And so it's 40. Yeah. A is the lower limit, and B is the upper limit. So you're going from smaller, well, not smaller. This is the first one and the second one. So A is equal to -1, b is equal to 3. And if you put it in backwards, you'll get a negative answer. Ready? Oh, sorry. Okay, now let's do the next one. These two are geometry problems. You don't have to do rectangles. You do one big rectangle. What is my function here? F of x equals what? Pi over 2. And that's approximately 1.57. It's a constant, so it's asking to find the area under the curve between -4 and -1 under pi over 2. So I'm going to draw a picture here. And here's -4, here's -1, and pi over 2 is some sort of horizontal line. That wasn't very good. Oh no. Sometimes that happens. Yeah, but try it. There, that's better. That's pi over 2. It doesn't really matter what it looks like. There's -4. There's -1. And I want this part in here. Well, that's easy. Just geometry. It's just a rectangle, right? So it's the base. How big is the base? 3. And then the height is pi over 2. So the area is going to be equal to 3 times the height, but that's pi over 2. And you could do 3 times 1.57, but we don't really care. So if you can do geometry, do geometry. Remember those words, because you're going to try and do some other crazy things when I show you the calculus. But you can do geometry. You can always do geometry if you can do geometry. Okay, how about that one? Anybody know what that looks like? Well, it's y is equal to the square root of, it's a circle, yeah, 16 minus x squared. How do we know it's a circle? Let's square both sides. So y squared equals 16 minus x squared. And then I'm going to add x squared to both sides. So we're going to get x squared plus y squared equals 16. There it is. And they won't have anything complicated. They won't have a circle centered someplace other than the origin. And what's the radius? 4. Okay. So let's graph this. It's a circle centered at the origin with a radius of 4. So that's 4. That's -4. And we are going to find the area between -4 and 0. So -4 to 0 is this piece right here. What fraction of the circle is it? It's a fourth. So it's 1/4 the area of a circle, which is pi r squared. Okay, so I don't need any calculus. I'm just going to use geometry. So it's 1/4 pi, and the radius is 4. So the answer is, that's 16 divided by 4 is 4 pi. That's all there is. Do you guys know why you don't have the bottom part of the circle? That's too bad the square root's always going to be positive, or non-negative, I should say. Yeah. Okay. So just going to do geometry. So if you remember your final exam, you'll maybe remember you had some geometry and that we had to throw that part. I mean, I didn't ask you the question, but that's what you'd be doing, just finding the geometry, finding the area using the geometry. You do have to be careful about which direction you go. If I integrate the wrong direction, I will get a negative sign. So it's like a vector. Okay, some properties here. And you just don't worry about the words. All the first one is saying is, what if I found the area under the curve from A to A? What's that going to give me? What's the area under an infinitely small point? 0. And the other thing is if I'm going to go from A to B, and I switch it. So if I have the area from A to B, and then I switch and I want to go backwards, b to a, what's going to be true about the sign? What do you think? It's going to be negative. It makes a difference. And don't worry about all the fancy words. When they say something's integrable, you can integrate it. And the deal is you can integrate it as long as it's just a finite number of breaks in the graph. You may not integrate over an asymptote. So if I wanted to integrate 1 over x, and then I put a little dx there, from negative 1 to 1, I've got a problem where it's 0, because this looks like this. And some of you are going to say, well, those areas will just cancel each other out. No, they don't. Not necessarily. So, I can't do this. It's called an improper integral. So you can't integrate over asymptotes. Make sure you find out how you can do it. Okay, what do we got here? So you can integrate functions that are not continuous. Not every single thing can be done, but more things can be done. You could do it for if it was a discontinuous piece. Also, polynomial functions are integrable. What's a polynomial function? Remember? Like ax to the 4th plus bx cubed. Those exponents are nice whole numbers. No fractions, no negatives. But so you can integrate anything that looks kind of like that, polynomials, sine and cosine, the trig functions. You can integrate rational functions provided the integral contains no points for the denominator is 0. So I can't integrate 1 over x over 0. That's a problem. And we're not going to worry about that because those are improper integrals. And I think we're almost done. Okay, a little bit more. Yeah, this was a huge day. We warned you it would be. Okay, if I have an odd function, do you remember about odd even functions? I'll do a cubic, that's an odd function. And I want to find the area from minus a to a. Okay? Look at the picture. Remember, it's a signed area. So I should be careful about how I say it. I want to find the integral from minus a to a of an odd function. What do you think the integral is? 0. So when you see limits on these a's and b's, and if they are equal but opposite, then you're looking for maybe it's an odd function because it's 0. So I could give you the sine function. Is that even or odd? It's odd. From minus pi over 2 to pi over 2. That's pi over 2. And that's minus pi over 2. That's true about the sine function. So I wanted to integrate from minus pi over 2. I don't have to do any work to pi over 2. What's that answer going to be? 0. Because these pieces cancel each other out. Now, that's not to say the real area is 0. It's not. Now, you remember how you know if you have an odd function? That f of minus x? Yeah. I like the odd ones. The even ones are okay, but they're not nearly as easy as the odd ones. Remember the even ones? Like y equals x squared. That one. And if I have f of minus x, that's equal to minus f of x. Nope, sorry. I mean positive. Wait. So what if I try to add those areas up from minus a to a? I'm not going to get 0, I wish. I'm going to get what? I'm going to get 2 times my integral from 0 to a of f of x dx. Let's start using it right now. So I went through a lot of work that's complicated and difficult, but the homework isn't meant to be difficult. And it says right up here, right here on this line, you're going to use geometry or FNINT, and I think they tell you that on your calculator. So what we did is, let's go back and let's see what we did. We did a lot. Let me go through it, and then I'll show you that again. First we started with, just a regular quadratic curve, and we took two rectangles, said, that wasn't a very good estimate, was it? So then we did 4, got better, but not good enough. Then I said, well, what if we go to an infinite number of rectangles and just shade the whole thing in underneath? And that will get us the exact answer, actually. But you have to know what this summation of I squared is. It might be a 2n. I don't know, I just see it. Okay, and so then I said, we called it an integral. Riemann said, all that stuff of adding those rectangles is a pain. I don't want to write all this. So he made his own notation, and he wrote it as an integral, and that's what you mean by an integral. Just let's find the signed area under the curve. That's all it is. And we can do that with geometry or with our calculator. And you can read through that, but it's basically the same thing. And so what you're going to have to do in the exam is take something like example 1 and change that and realize, oh, that's just the integral of that. And you'll be able to do that the easy way. We haven't done it yet, but we will. And then the other way we did it was with geometry. So that's all you're going to have to do is use FNINT or geometry. You just have to know that that little symbol there means integrate. Find the signed area under the curve. There's a lot of good stuff there. But you have to think about it. What do you really have to know? Not a lot. Just what that integral means. And then you'll be okay. Oh, and then the last slide was, we can make our life easy if we have even and odd functions. Well, even doesn't help too much. It helps a little bit, though, because sometimes even working with the negative numbers is a pain. So if I could do that, I'd rather go 2 times 0 to 8. So you look at the homework, and we could still have like 8 minutes. We could try some of those homework problems. And I could answer questions. You should be working on this big packet. You should have done a couple problems already, at least 2. There were a total of 6. So, you know, if you did 2 more today, eventually you're going to get it done. And you check answers, they are online. But you do need Smartboard software. Yeah. You should have had all your packets from before, though. Oh. Oh, you missed that one. Yes. Okay. Okay. You can have this one. Oh, okay. Over there. Okay, you should. Somebody said, are you going to collect them? Well, you know, I shouldn't have to do that because you need to do that. Yeah. There it is. Yeah, big packet.
That be out of something on basic calculus, but I wasn't here on Friday. So
Oh, maybe I put it in the wrong place. So it's somebody else's. I'll have to figure that out. Thank you. Oh, thought I stopped.